Hey everyone, and welcome to this explainer. Today, we're diving into a massive, high-stakes topic in AI news, the real-world reliability of medical AI models. We hear constantly about these deep learning models hitting superhuman accuracy in medical imaging, right? But honestly, there is a hidden crisis in how these models are evaluated, and it could seriously impact patient safety.
So here's the central mystery we're going to solve today. Why is it that a medical AI model can score perfectly in the lab, but the second you deploy it in an actual hospital down the street, it just suddenly breaks and fails? The answer to this completely flips everything we know about building and validating medical AI.
Okay, let's dive into our roadmap for today. We're going to cover 1. The medical AI illusion, 2. The dataset shift problem, 3. The cross-dataset benchmark, 4. CNNs versus transformers, 5. Why architecture matters, and finally, 6. Building safer medical AI.
Let's start with Section 1, the medical AI illusion, lab success versus real-world risk.
You see, right now, the machine learning community is making a really dangerous assumption. They're assuming that controlled lab metrics guarantee clinical safety. Medical imaging papers routinely blast out these sky-high accuracy numbers. But there's a huge catch. They almost exclusively train and test their models on the exact same dataset. This is called in-domain testing. It's totally predictable, and it generates those flashy reports you see in the headlines. But clinical deployment, that's a whole different beast. Out in the real world, models face brand new conditions, different sensors, and they suddenly degrade. So this single dataset testing is essentially just masking the actual real-world risks.
Moving on to Section 2, the dataset shift problem, the hidden enemy.
So what's actually breaking these models? Well, it's something called dataset shift. Formally, dataset shift is the degradation in a machine learning model's performance when the real-world data differs in distribution from the data it was trained on. Simply put, if your model learns to spot a disease using images from hospital A, and then you ask it to look at images from hospital B, the underlying data is different and the model just gets incredibly confused.
To really put this into perspective, think about the specific variables that cause this shift in a hospital. You've got different camera sensors from clinic to clinic. The lighting in an exam room might be harsh fluorescent instead of natural light. The physical traits of the patients, like unique wound morphologies, can vary depending on where you are. Even the software's pre-processing pipelines can differ slightly. Literally, any single one of these variables can cause a shift that completely derails a supposedly perfect AI.
All right, Section 3, the Cross-Dataset benchmark, the experiment. A really fascinating recent study on archives actually set out to measure exactly how bad this problem is, specifically looking at diabetic foot ulcer segmentation. Now, what's really interesting here is the 3 gladiators they chose to step into the testing arena. First up, UNet, which is a low-complexity convolutional neural network, or CNN. Next, they brought in DeepLab v3+, a much higher complexity CNN. And finally, Segformer B2. This one is high complexity too, but it's fundamentally different. It's from the Transformer family.
To put these models through the ringer, the researchers set up a brutally strict evaluation protocol. It was designed specifically to prevent data leakage and expose the absolute true ceiling of how well they generalize. Here's how it worked. Step 1. Train all models on a combined dataset from 2 specific sources, FuseEgg and AZH. Step 2. Test them zero-shot, meaning they've never seen it before, on a completely independent external dataset called DFUC 2022. Step 3. Test them zero-shot again on another external dataset, Metatech. And crucially, no fine-tuning was allowed at all. This was a raw test of adaptability in an unknown clinical setting.
But before we see how they did in the wild, let's look at their lab scores. On the in-domain test, meaning data from the exact same sources they were trained on, all 3 crushed it. They scored between 0.80 and 0.83 on the DICE score, which is a standard segmentation accuracy metric. Looking at these numbers in a vacuum, you'd absolutely think all 3 were ready for prime time.
But we know better than that now, right? Section 4. CNNs versus transformers, the showdown.
Once those training wheels came off and they faced independent data on the DFUC 2022 dataset, performance dropped across the board. But it wasn't equal. UNet managed a moderate score. DeepLab v3+, despite being this highly complex powerhouse, completely crashed and burned with a super low score. But the Transformer, Segformer B2, it massively outperformed the CNNs, securing a much higher cross-dataset DICE score of 0.557.
This brilliantly illustrates something I like to call the myth of complexity.
A lot of developers just naturally assume a heavier, more complex model is going to handle real-world messiness better, but the data proves that's totally false. The complex DeepLab v3 Plus actually generalized worse than the much simpler UNet model. More complexity does not automatically equal better performance across domains.
And honestly, average scores don't even paint the full picture. When you dig into the per-image failure rates, the clinical risk is genuinely terrifying. In this context, a catastrophic failure means the model got the segmentation completely wrong. On the external dataset, the highly complex CNN DeepLab v3 Plus failed catastrophically on a staggering 43% of images. UNet hit 38.5%. Segformer B2 had the fewest at 31.1%. Guys, this difference in failure rates is literally the difference between patient safety and complete loss of doctor trust.
Now you might be thinking, was this just a fluke on one dataset? Nope. The researchers validated this across 2 independent external sources, analyzing a massive 2,160 external images. And they confirmed the results using Wilcoxon's signed rank tests with a p-value of less than 0.001. That means these findings are highly statistically significant. Without a doubt, the transformer consistently beats the CNNs on unknown data.
So why? Section 5. Why architecture matters. The mechanics. Let's look under the hood.
It all boils down to how these architectures actually see an image. CNNs rely on local receptive fields. They focus on tiny, localized patches of pixels to find patterns like edges or textures. But what happens if the lighting changes? Those local pixels suddenly look completely different, and the CNN gets completely lost. Transformers, on the other hand, capture long-range spatial dependencies and global context. They process the relationships between different parts of the entire image all at once. That broad, holistic view is exactly what makes transformers so much more resilient when local imaging conditions inevitably shift.
In fact, the central thesis of the entire paper hits the nail on the head with this quote. Architecture family, not model complexity, drives cross-hospital generalization. It's not about how deep or complex the model is. It's about the core mathematical structure you're using to process the data.
Okay, Section 6, Building Safer Medical AI. Actionable takeaways. Whether you're an AI developer, a practitioner, or running a hospital, you need to adjust your strategy today. First, stop trusting single dataset dice scores. They're just an illusion. Second, you absolutely have to implement external zero-shot holdout evaluations. Third, prioritize transformer-based architectures like Segformer when you're moving to clinical deployment. Fourth, stop just looking at the averages. Track those catastrophic failure rates per image so you know your tail risks. Fifth, audit your dataset provenance, document the lighting and sensors. And finally, automate your cache and dependency management to avoid any silent configuration drift when you're swapping architectures.
So the crucial point to take away is this. Dataset shift is the primary bottleneck keeping medical AI out of clinics right now. But your choice of architecture, specifically choosing the global context of a transformer over a local CNN, is the absolute best lever you can pull to mitigate that shift and build AI we can actually trust.
I want to leave you with a question to chew on. If the basic assumption that complex models generalize better has been proven completely false in medical segmentation, what other AI deployment assumptions across the entire industry are we currently testing completely wrong? It is definitely time to interrogate our validation methods. Thanks for joining me for this explainer. Keep asking the hard questions, and I'll catch you next time.